So I posted the practice exam 2 online, right? So in the practice exam 2, you're going to have only 2 questions. The first one will be about finding eigenvalues and eigenvectors, right? So you're going to have to go through all of these characteristic equations. You try to solve 3 cases. In one of the three cases, you will have a lot of eigenvalues and eigenvectors, and this is what you have to do. So in the first one, it is a little bit harder than what we did in class. In the practice exam, the first exercise in the practice exam was a little bit harder than what we did in class because the characteristic equation has 3 coefficients. You have x squared plus ax plus b. It's the full equation. It's not x squared plus lambda anymore. And then you're going to see that, okay, when lambda is greater than 1, you have a series of eigenvalue and eigenvectors, right? It's not just lambda greater than or equal to 0. And for the last one, you're going to have to use eigenvalues and eigenvectors to solve the boundary value problems. So basically, in the second problem, you will see the Fourier series, right? So when you solve the eigenvalue and eigenvectors, you're going to see the Fourier series, and you're going to use this Fourier series basis to solve, to expand the Sox term and then to solve the equation, all right? So you go through everything during the spring break, and after the spring break, I will try to solve the practice exam for you. Any questions? Yes?
So how many questions is the actual exam going to be?
2.
2.
It will be exactly like in the practice exams, right? So you see the practice exam 1 and the real exam 1, right? So the practice exam 1 is harder than the real exam, and it's going to be the same. For the practice exam 2, you're going to have 2 questions. The real exam 2, you also have 2 questions. The practice exam 2 is harder than the real one, so that you practice, and it's better that you practice something harder, and then in the competition you do something easier. Other questions?
When is the exam?
I think this is the Friday after spring break. All right, so you're going to have the whole spring break to do these 2 problems, and we're going to solve those problems before the exam, and then so that you get ready for the exam on Friday. Other questions? It's clear? All right, so let us continue our previous lecture, right? So in the previous lecture, you have uxx is -1, and you try to solve the equation on 0 and 1. All right? And then you have 2 boundary conditions that u0 to be 0, u1 x u1 is 0, right? So this is Dirichlet, and this is Robin, right? So in the previous class, what we were trying to do was to try to solve the eigenvalue problem, right? So this is step number 1. Step number 1. So solving the eigenvalue problem. All right. So what is the eigenvalue problem? So the eigenvalue problem will be the same. So you have this is equal to 0 on 0 and 1. And you have the same boundary condition. U0 is 0. And phi 0 is 0 plus phi 1 plus phi prime 1 is 0. All right. So this is the eigenvalue problem that we were trying to solve. So for this eigenvalue problem, in the previous class, we looked into the characteristic equation. Lambda squared plus lambda is equal to 0. Right? So this is the characteristic equation. So we consider 3 cases. Case number 1, lambda is negative. So only trivial solution. All right, and case number 2, you also have trivial solution, right? All right. So I explain again. So this is the kind of equation that you have in the practice exam as well. So I give you boundary value problems. So you have Laplace is equal to the source term. Here you have -1. All right. So you have two boundary conditions. The first one is Differential. The second one is Robin. So you have u1 plus ux of 1 is 0, and this is Robin, right? So to solve this equation, so this is basically problem 2 in the exam. Questions 2 in the exam. All right. So so basically this is question 2 in the exam. So in order to solve this equation, you have to remember 3 steps, right? The first step is to try to find the eigenvalue and the eigenvector. All right. So so this is basically the eigenvalue problem, right? So you have this Laplace operator plus lambda phi is 0, and you have the same boundary condition. So you have this boundary condition is moving here, and this boundary condition is moving here. It's clear? Questions? So to solve this equation, this is a second order differential equation with constant coefficient, right? So this is the previous class knowledge. So in order to solve this, we know that we have a characteristic equation x squared plus lambda is equal to 0, right? But you don't have to go back to the previous class, because in the very first lecture of the chapter, I gave you all of these formula, right? So you go back and you have to remember all of these formula. So you have x squared plus lambda is 0. There are two cases. If lambda is negative, you have a trivial solution, and if lambda is 0, you also have a trivial solution, right? So this is what we did in the previous class. Case number 3. So you have lambda is positive. So when lambda is positive, you have x squared is minus lambda. So you have 2 roots, right? So root number 1 is I times square root of lambda, and root number 2 is minus I times square root of lambda, right? So when lambda is positive, so x squared is minus lambda, right? Then you have 2 roots. The first one is I square root of lambda, and the second one is minus I square root of lambda. Questions? So now you have 2 solutions. You have u1 is cosinus of square root of lambda x, and u2 is sinus of square root of lambda x. All right? It's clear. So this is also in the formula that I gave you in the first lecture of this chapter. All right. Right. So you have 2 solutions associated to the roots of the characteristic equation. So then you're gonna have the general form of phi will be phi x is c1 cosinus of square root of lambda x plus c2 sinus of square root of lambda x. All right. So this is the general solution, right? So when you solve x squared is equal to minus lambda, you have 2 solutions, I square root of lambda and minus I square root of lambda. All right. Then you have cosinus square root of lambda and sinus of square root of lambda, right? So the solution will be the linear combination of u1 and u2. So now you have to compute c1 and c2. All right. So now you have boundary condition. So the first boundary condition is phi 0 is 0. Phi 0 is 0, which means that you have c1 cosinus of square root of lambda times 0 plus c2 square root of lambda times 0 is 0. All right? Right? So the first case is phi 0 is 0, which means that sinus c1 times cosinus of square root of lambda times 0 plus c2 times sinus square root of lambda times 0 is 0, right? So I'm going to replace this by 0 and this by 0. Alright? It's clear? So this is 1 and this is 0. So which means that C1 is 0. It's good? Questions? So this is always this is the same procedure that you have to go through to in order to solve the eigenvalues problem, right? So you go through the characteristic equation, you consider 3 cases, and you plug into the boundary condition to find all of the constants. So this is the general mechanism. So now you have C1 is 0. So the next will now be C2 sinus of square root of lambda x, right? That's clear. So now I'm gonna have to compute the derivative because here I have phi prime at 1, right? So which means that phi prime of x will be C2 square root of lambda cosinus of square root of lambda x. All right? It's clear. So I explain again. So you have what? You have phi 0 is 0. Because phi 0 is 0, then I replace 0 here. I have C1 cosinus of 0 plus C2 sinus of 0, and this is 0. All right? So this is 0, and this is 1, which means C1 is 0. So because C1 is 0, phi x will be C2 sinus of square root of lambda x, and this means that phi prime is C2 square root of lambda x cosinus square root of lambda x. It's clear? All right. All right. So now I'm gonna replace 1, right? So you have phi 1 plus phi prime at 1 is 0, which means that C2 sinus of square root of lambda plus square root of lambda C2 cosinus of square root of lambda is 0. So sinus of square root of lambda plus square root of cosinus of square root of lambda is equal to 0, right? It's clear. So I explain again. So now you plug 1 into phi x and phi prime of x, you get C2. So you plug 1 here, you have C2 sinus square root of lambda. Here you have C2 square root of lambda cosinus square root of lambda, because here I plug 1, right? So I have the 0. So which means that I have sinus square root of lambda plus lambda cosinus lambda is 0, right? So here I don't accept C2 to be 0, because if C2 is 0, C1 and C2 are both 0, and you have a trivial solution, right? C2 can be 0, but in this case, C1 and C2 is 0, and you have trivial solution. All right? So in this case, I don't accept. C2 to be 0, because if C2 is 0, then both C1 and C2 are 0, and then you have trivial solution. And this is not an eigenvectors, right? So 0 is never an eigenvector, eigenfunction. But 0 can be an eigenvalue. Right? Questions? Right, so now the equation will become this one. Right, so this one is not easy to compute. So you don't have formula like P over N like in the previous case. So here in the note, we computed a few. For you, for instance, you have numerically. You can compute square root of lambda 1 to be 2.0 2876 square root of lambda 2 will be 4.9, 318, etc. Square root of lambda 3 is 7.9, 7, 8, right? So basically, so finally, so the eigenvalue lambda n are not do not have explicit form. So we just denote them by lambda n, which are solution of sinus of square root of lambda n plus square root of lambda n cosinus of square root of lambda n. Right? So different from the previous case. In this case, you don't have explicit forms for lambda n. So of course, in the exam, I will ask you to do this, but in reality, you will have this kind of situation. So you can compute lambda 1, lambda 2, lambda 3 using MATLAB or the computer, but in principle, you don't have the general form for them. So we just say that, okay, these are the eigenvalues, and you have a sequence of them. Those eigenvalues satisfy this equation. That's it. All right? It's clear? Questions? All right. So, yes?
In this case, how many is n going to infinity?
N is going to infinity. So it's like in the previous case, you also have infinite eigenvalues and eigenvector, and you can expand them in the basis, right? Why? Because the operator is never joined. So I'm gonna check this operator is never joined, and the operators of the previous class that I promised to check. So I'm gonna check both at the same time, right? It's clear. All right. So in this case, the eigenvalue, the eigenfunction will be eigenvector. It is also called eigenfunction, right? Because they are function. So you're gonna have Phi n. So you have C2, C2, right? So you have Phi n of x will be sinus of square root of lambda n x. All right. So, you have questions for this? So I explain again. For this case, it is a little bit different from the previous case that you don't have the explicit form for lambda n. You can compute like lambda 1, lambda 2, lambda 3. So you can compute that using the machine, right? However, in this case, you don't have a general form. So what? So basically, I explain again. Step 3, case 3. So you have x squared is minus lambda. So you have two complex solutions. The two complex solutions give you cosinus and sinus. So then this is the general form of a solution, right? The key now is to compute C1 and C2. So how do you compute C1 and C2? You're going to plug in the boundary condition. So the boundary condition is 0 gives you C1 cosinus of 1 of 0, which is 1, and C2 sinus of 0, which is 0. So this is 0, which means that C1 is 0. So this means that phi will be only the sinus function because C1 is 0. So now I'm going to take the derivative of phi. I get C2 square root of lambda cosine square root of lambda, right? So I'm going to check the second boundary condition. So you have phi1 plus phi prime 1 is 0. So I have C2 times sine square root of lambda, C2 square root of lambda cosine lambda is 0. All right? So which means that C2 of this is 0, but I don't accept C2 to be 0 because if C2 and C1 are both 0, you have a trivial solution. And if the solution is trivial, this is not an eigen function or eigenvector, right? So basically this is the equation that we have. But we cannot do further than that. Like in the previous case when you don't have this term, for instance, you can say that lambda is n pi or something like that. But here you cannot say anything. So you can compute lambda 1, lambda 2, lambda 3 to lambda infinity. But you have to do you have to use the computer and do it step by step. So I'm gonna keep this equation here, and I'm gonna say that the eigenvalues are the solution of this equation, right? And eigenfunction will be this one. So there will be no C2 because in the eigenfunction or eigenvector you can throw away the constant. It's clear? Questions? Yes?
Throw away the C2 because it's arbitrary, right?
C2 can be anything.
Yeah.
So it's like the basis, right? So in the basis vector, you can divide or multiply by constant. So basically, this is also a basis. Other questions? Yes?
Why does the eigenvector only include sine and not the cosine term?
Because here you see that, okay. Because here you see that C1 is 0. So C1 is 0 means that the eigenfunction or eigenvector is only C2 times sinus. Right? So you have C1 and C2. Alright? So you plug 0 here, you find that this is 1, but this is 0. So this is 0, it is fine, but this means that C1 is 0. So C1 is 0 means that the eigenvector, the eigenfunction, has no term like this because C1 is 0. Alright? It's clear? Other questions? Right, so now if there is no questions, again, we're gonna solve the equation, alright? Step number 2. So you're gonna have to expand minus 1, right? Minus 1. Expand minus 1 in terms of sinus of square root of lambda and x. All right. So you're gonna have a formula which is similar to the for a series. So you have minus 1 is the sum when n is going from 1 to infinity of fn sinus of square root of lambda and x. All right. Right? So how can I compute fn?
Use those diagonality.
Yes. You use no power. Can you sign it back? Right, so you can compute fn using the formula, which is the following. So you have fn will be minus 1 sinus of square root of lambda n x, and we divide by sinus of square root of lambda n x, sinus of square root of lambda n x. All right. Right. So basically, this is the formula that we have, which is similar to the formula in linear algebra. Right? So the coefficient fn will be the inner product of 1 times this eigenfunction or eigenvector, and you divide that by the eigenfunction eigenvector squared. It's clear? So now I have to compute that, right? So I have the integral from 0 to 1 of minus 1 times sinus of square root of lambda n x dx. Alright, so what is it? So this is the first integral. So this, I'm gonna move the minus outside, so I have the integral from 0 to 1 of sinus of square root of lambda n x dx. Alright? It's clear? So this is the first one. So this is inner product of minus 1 and sinus. Alright, so this is the integral from 0 to 1 minus 1 times sinus. So I'm gonna move minus outside, I have the sinus. So now what I have to do is to do the antiderivative of the sinus only, right? So the antiderivative of the sinus will give you cosinus, this is minus cosinus square root of lambda n x dividing by and you take the difference between 0 and 1. Alright? So in order to compute this integral, right? To compute this integral, you're gonna take the antiderivative of sinus, which is cosinus. But you have to divide by the factor of square root of lambda. And you have a minus, and outside you have a minus, another minus. So now what I have is, I have two minus, so I don't have anything to worry about. So I have cosinus of square root of lambda n minus 1 dividing by square root of lambda n. Alright? It's good? So I explain again. So now I have to compute the coefficient Fn, right? So how do I compute the coefficient Fn? I'm gonna multiply minus 1 with sinus and I'm gonna divide sinus squared. So here I have the interval from 0 to 1, minus 1 sinus dx, alright? So I'm gonna move the minus outside, I have only the sinus. So the antiderivative of sinus is cosinus, so I have minus and minus, I can forget about that. So now I replace 1 here and 0 there, so I have this. It's good? Now, I'm gonna have to compute the second one. So I have sinus square root of lambda n x squared dx. Alright? So here I have sinus squared. So what formula should I use?
1 minus cosine 2.
Excellent. Can you say at the back of the paper, please? So I have sinus x squared will be 1 minus cosinus of 2x divided by 2. Alright? So I'm going to use this formula here. So I'm going to have integral from 0 to 1. 1 minus cosinus of 2 square root of lambda n x dividing by 2 dx. Alright? So this is the formula that I'm using. So sinus x squared will be 1 minus cosinus 2x divided by 2, right? So you have sinus squared, and this is 1 minus cosinus 2 times square root of lambda x divided by 2. So again, the first one, I'm gonna have x over 2, and I take the difference between the two limits, 0 and 1, alright? The second one is minus cosinus plus 1/2 minus 1/2 of cosinus. Cosinus of 2 square root of lambda n x dx. Alright? It's clear? So I explain again. So here I have sinus squared. So sinus squared will be sinus x squared will be 1 minus cosinus 2x divided by 2. Alright? So this is going to be 1 minus 2 times cosinus square root lambda n x divided by 2. Right? So the 1 has the antiderivative which is x over 2, and I take the difference between the two boundaries, the two limits. And now the leftover is the cosinus, and of course the cosinus has the antiderivative which is what? Sinus, right? Can you say at the back of the paper, please? So the cosinus has an antiderivative of, so this one will give me 1/2 minus 1/2. So I have sinus 2 square root of lambda n x dividing by 2, right? Square root of lambda n. And I take the difference between 0 and 1. Alright? So I have minus 1/2 minus 1/2 of So I have sinus of 2 square root of lambda n minus 0, so this is 0. So I have 2 square root of lambda n, and this is 1/2 minus sinus of 2 square root of lambda n dividing by 4 square root of lambda n. Alright, so this is formula. So now I combine this formula and this formula. Alright, so and I'm gonna have Fn will be cosinus of square root of lambda n minus 1 dividing by square root of lambda n. Alright? And this is dividing, so this is giving me 2 square root of lambda n minus sinus of 2 square root of lambda n dividing by 4 square root of lambda n. So I'm gonna divide by 2 square root of lambda n minus sinus of 2 square root of lambda n dividing by 4 square root of lambda n. And this is 4 times cosinus of square root of lambda n minus 4 dividing by 2 square root of lambda n minus sinus of 2 square root of lambda n. Right? It's clear? So I explain again. So the first thing that I have is this formula, right? Which is this one. And this gives me this constant. Alright? It's clear? So the second one is this one. Alright? So this inner product of sinus and sinus will be computed here. And the solution is 1/2 minus sinus of 2 square root of lambda n dividing by 4 square root of n. And this is basically 2 times square root of lambda n minus sinus of 2 times square root of lambda n divided by 4 square root of lambda n. Alright? So, in order to compute Fn, I'm going to have to divide this one and this one. Alright? Which means that I have to divide this cosinus, which is here. Alright? So I'm going to put this here. Alright? And I'm going to divide this with this guy. Right? So this guy is 2 square root of lambda n. So 2 square root of lambda n. Sinus of 2 square root of lambda n divided by 4 square root of lambda n. Right? So when I divide, the square root here and the square root here disappear. So I multiply 4 here and have 4 times cosinus square root of lambda n minus 4 dividing by this one 2 square root of lambda n minus sinus of 2 square root of lambda n. Right? This is a lot of calculations and mistake can happen everywhere. So you have to be careful, right? So questions on this? Yes?
Is that 8? What's next to the 8 right there, the bottom right, the last result?
This one?
The denominator, the last one?
This one?
Very last one.
This one?
Yeah.
This is 2, right? This is sinus.
Oh.
Right? So this is going from here, right? So this is sinus. This is sinus. Alright? So I explain again. So this is the result when you compute the first interval, the first inner product. So you have to multiply minus 1 with sinus, and this is an inner product, right? So which means that you have to take the interval from 0 to 1 of minus 1 sinus dx, right? Right. So now you have to compute this interval. So what I do is I put minus outside, I have sinus. So the antiderivative sinus is cosinus. So I'm gonna compute this, and I got this quantity, right? The second one will be sinus, times sinus, right? So sinus in a product with sinus. So I have the interval from 0 to 1 of sinus squared, which is using this formula 1 minus cosinus of 2 times. So here I have square root of lambda n x. So I have 2 times of that. So I have 2 square root of lambda n x divided by 2. Right? So the 1 is going out. So I have x over 2 difference from 0 to 1, have minus 1/2 and have cosinus. So cosinus here has the antiderivative, which is sinus. So I try to compute that, and this is the final result, right? So what I do is I divide this term and the final term, and when I divide this one and this one, I get this answer, right? Questions? It's clear? Right, so step number 3. So now you have all of the coefficients, right? So now you have that Fn, and so you have Un will be minus Fn dividing by lambda n, which is minus, so I have U, the solution will be somewhere, and this is step 3. Un times sinus of square root of lambda n x, right? So Un will be Fn over lambda n, and this is minus 4 cosinus of square root of lambda n x, minus 4 dividing by 2 square root of lambda n minus sinus of 2 square root of lambda n, and then you divide the whole thing by lambda n. Alright? And this is gonna give you, right? So I explain again. So in the last step, you expand U into Un times all of the eigenfunction or eigenvectors, right? So you have Un, which is the coefficient, and this is the eigenvector that you just found, right? It's clear? So now, after you found this, Un is the unknown. You want to compute the Un, right? Un is the unknown. And U is also the unknown. Right? So in order to compute Un, you're going to divide Fn by lambda n, and you take the minus. So this is the formula that we found in the previous class. So minus Fn will be this quantity that I just found here. So I have minus 4 times cosinus square root of lambda n, minus 4 divided by 2 square root of lambda n minus sinus 2 times square root of lambda n. And I divide everything by lambda n. Again, lambda n do not have an explicit formula. You know that the lambda n are solution of an equation, but we don't have the explicit formula for lambda n. So you have this. Then you have lambda n times 2 square root of lambda n sinus of 2 square root of lambda n. Right? And again, lambda n is the solution of, again, lambda n is the solution of sinus square root of lambda n plus square root of lambda n cosinus square root of lambda n is 0. Alright?
Are you missing a negative in the numerator?
This is no, because I have minus here. So I just change for I put, so this become a plus and this become a minus. So I have
Okay,
this
never
one.
mind, minus it now.
And so
Alright.
finally I have this.
I see now, sorry.
Yes, I just multiply lambda n to this formula. Okay, right? Other questions? It's clear. So I gave you a lot of examples, and I try to go over all of them so that you understand this method of eigenvalues and eigenvectors, how to use them to solve value problems, right? And you're gonna have to deal with those kind of things in the midterm. So again, I have to check the sample choice, right? Other questions on this kind of, yes?
What is the equation that box 1, the column?
So this one.
Yeah.
So this is the equation. so after step 3, right? After case 3, so lambda n is the solution of this one, right? So you remember that after step 3, you have phi, which is C1 cosinus of square root of lambda x plus C2 sinus of square root of lambda x, right? This is what we have in case 3. So you have phi 0 is 0, which means that C1 is 0, right? This is the first boundary condition. So the second boundary condition is phi 1 plus phi x of 1 is 0. And this gives you this equation. So I said that this equation is not, the solution of this equation are not explicit. But we know that there are a finite, an infinite number of lambda n such that this is satisfied. And they will be value of our problem. Right? It's clear? So in the step 3, because lambda is positive, so you have two roots that are complex. So that gives you this general form of the solution, right? And then you plug into the boundary condition. So the first one gives you C1 is 0, and second one gives you this one. Other questions? It's clear? It's fine. Yes?
So, is that the form we're writing our final answer in for like having finished all 3 steps?
So this is UN. This is the final answer.
For UN, right?
This is what you have to solve, right? And you have a final answer.
Right.
You don't have actually explicit form for lambda n.
Right.
So you can just say that, okay, lambda n solve this equation, right?
Okay, so when we like write in our final answer, like we're establishing our UN is that, and we're defining what our phi or our lambda n is equal to by that.
Right.
Okay.
Other questions? It's clear? So you understand how to use the method, right? Now, why are they working? Because they are self-adjoint. So again, I'm gonna check 2 examples. This example and the previous one. And I'm gonna check that those are self-adjoint operator, right? So this example is complicated because the form of lambda n is not given, and the formulas are also not easy to compute. All right, so in the previous class, we were trying to solve this one. Uxx is minus 2, all right? And you have u0 is 0, and then you have u1 plus ux of 1 is 0, right? So this is the previous example. Right, so this is the previous example, all right? And I'm gonna check self-adjoint, right? So in order to check self-adjoint, I have to show that uxx of v interval from 0 to 1 dx is also equal to interval from 0 to 1 of vxx u dx. The condition here are the following: u0 is 0, u1 plus ux of 1 is 0, and v0 is 0, and v1 plus vx of 1 is also 0, right? So this is self-adjointness. This is what we have to check, right? So in order to check that this is self-adjoint, you're gonna pick u and v. You're gonna show that uxx times v is vxx times u under the condition that they satisfy the same boundary condition, right? u0 is 0, u1 plus ux of 1 is 0, and v0 is 0, v1 plus vx of 1 is also 0. Questions? Right, so this is very easy because you're gonna do integration by part, right? So you have uxx v dx will be ux v different from 0 to 1 minus interval from 0 to 1 ux vx dx, right? So this is integration by part. So what do you have? You have the formula that I'm using is a dp is ab minus b dh, right? So this is a, this is b, right? So this is integration by part. So in order to check Selberg choice, I'm going to integrate from 0 to 1. You have use xx v dx, right? Is uxv, the difference from 0 to 1, minus interval from 0 to 1 of ux vx dx, right? So I'm going to compute this things, and I'm going to have ux of 1, v1 minus ux of 0, v 0 minus interval from 0 to 1, ux vx dx, right? So you know that v0 is 0, so this is 0. So this gives you ux 1 v1. All right, and this is interval from 0 to 1, ux vx dx, right? It's good. Questions? Explain again. So in order to check Selberg choice, you just have to do integration by part, and this is the basically the standard procedure, and then you plug in the boundary condition. So this is what I'm doing. I'm gonna integrate from 0 to 1 of uxx v dx. So I'm gonna use integration by part, which is a db is ab minus b dA. All right. So in this case, a is ux and b is v. So this is this is b and this is a. Right. So here you have db, and here you have a. Here you have b, and here you have dA. All right. So the integration by part formula is that a db is ab minus b dA. All right. So here you have the same. You have uxx, which is db, v is a. So then you have b dA, which is uxv, and here you have b dA, which is ux vx dx. Right? Questions? Now I'm gonna replace the boundary condition here. So I have ux at 1, vx at 1, minus ux at 0, minus vx at 0, minus the interval from 0 to 1 of ux vx dx. It's clear? So v0 is 0, so this is going away. So I have that term, right? So then I'm going to have to do another integration by part. So I have ux 1 v1 minus u vx interval from 0 to 1 plus interval from 0 to 1 of u vxx dx. All right? It's clear? So here I'm gonna use exactly the same formula, right? So this is dB, this is A. So this is B, this is A. So this is B, this is dA. All right? So again, I'm gonna use I use again this integration by part. I have a dB is AB minus B dA. So in this case, dB is ux, A is u vx, right? So then you have BA, so u vx, and then here you have B dA, which is u vxx dx, right? Questions? So we still have 1 minute, right? So you have ux 1 v1 minus u1 vx at 1 plus u0 vx at 0 plus interval from 0 to 1 u vx x dx. Right? So this is 0. Right? So after you compute, this becomes 0. So the leftover is this one. But with this one, this is also 0. So you just have to plug in this boundary condition. And you're going to see that this is 0. This gives you 0. Right? And you have a salvage join. For this the example today, you can also do the same thing. Right? So basically, in order to check salvage join, it is very easy. You just do integration by part 2 times. Right? For salvage join, what you do is integration by parts 2 times, and that's it. So in order to check salvage join, this is the only procedure that you have to do. You just integration by part 2 times, and it's automatically satisfied because the boundary condition will give all of the limit terms 0. Right, so we see after SMUMATH, yes?
What are those first terms canceling with 0?
So this one, right?
Yeah, okay.
This is 0.
Why?
Why? Because you plug this in and you see that, right? So what you see is the following. So you plug this and this in, you're gonna see that ux,
No, it works out as 0.
1 bx minus. The first term gives you this one. The second term gives you ux1, bx1. And this is so. Right? It's clear.